Good morning, students, and welcome to today's lecture. Please just put it on the chat if you can hear me, so that I'm sure that you can hear me. Okay. And welcome to today's lecture. Just put it on the chat if you can hear me, so that I'm sure that you can hear me. Okay, thank you very much.
Okay, so I think we can start. We have about 200 participants now, including the ones on YouTube. So the last time we met, we looked at thermochemistry.
I think we can start. We have about 200 participants now, including the ones on YouTube. So the last time we met, we looked at thermochemistry.
So we looked at thermochemistry and we looked at some definitions, work, heat, and some calculations. Okay.
So we looked at thermochemistry and we looked at some definitions, work, heat.
Okay. So today we are going to continue from where we stopped. So we are starting with endothermic and exothermic processes. Sorry, let me put them in slide. Okay.
So today we are going to continue from where we stopped. So we are starting with endothermic and exothermic processes.
So So for endothermic reaction, because of the word from the word endo, that means heat is absorbed inside. So energy is actually added to the system. So that is why we say heat is absorbed. And because heat is
reaction from the word endo, that means heat is absorbed inside. So energy is actually added to the system. So that is why we say heat is absorbed. And because heat is
sorry, I'm coming. I'm trying to check something. Okay. So as I said, in endothermic reaction, the heat is absorbed, so energy is actually added to the system. And because energy is added to the system, the reaction vessel is usually cool. Of course, for endothermic reaction,
energy is actually added. And because energy is added to the system,
and our Q is positive. And our Q is positive.
Endothermic reaction.
So for exothermic, heat is evolved. Heat is given out to the surrounding. So energy is removed from the system.
So for exothermic, heat is evolved, heat is given out to the surrounding. So energy is removed from the system.
Please, student, can you hear me? Because I'm having echo.
Having echo.
Uh-huh. So can you hear me now? Okay, that's fine. You can hear me now.
So can you hear me now? Okay, that's fine. You can hear me now.
So we have the diagram here. This is for endothermic reaction, and this is for exothermic reaction. So we can see for endothermic reaction, heat is given, energy is added to the system. So that is why it's usually positive and is cool. So for this, this is heat is given off to the
Heat is given, energy is added to the system. So that is why it's usually positive and is cool. So for this, this is heat is given off to the
I don't know why you can't hear me very well. I don't know why.
can't hear me very well. I don't know why.
So that is for endothermic and exothermic reactions.
Endothermic and exothermic reaction.
I'm trying to see what is causing this interference. I'm not using two systems, so I don't know why. Okay, I think we are good now. Let me close the other system. Can you hear me now? Okay, thank you. So that is for your endothermic and exothermic reactions. The difference between the two, one heat is absorbed and one heat is added. One is negative and the other is positive. And also one, the reaction vessel cools, while the other one, the reaction vessel is warm. So we look at internal energy. What do you mean by internal energy of a system? Internal energy of a system is the energy possessed by as a result of the spatial arrangement of its constituent atoms or molecule. What do we mean by spatial arrangement of its constituent atoms or molecule? That is, we are talking about the position and the organization of the objects in that given space or area, how they are arranged. And also, your internal energy is the sum of the kinetic and the potential energy. We've already known what our potential and kinetic energy is. Kinetic energy, energy in motion, while potential energy, stored energy at when it's at a particular place. And this energy, as we said, can be transformational, translational, rotational, vibrational. And I also explained to you that it can also be affected by temperature. So that is actually why you can have when we looked at kinetic energy and potential energy, the one that has that is affected by mass and velocity, especially the kinetic energy and also the temperature, because the higher the temperature, the higher the rotation. Okay. So for the internal energy, it is not very easy to determine the absolute internal energy. So most times, what you try to determine is actually the change in internal energy. And this change in internal energy, you can only experience it when the system undergoes a process. So we normally say the process is more useful thermodynamically and it's easier to obtain. So just obtaining the internal energy of a system is not possible. But when you now look at the change in internal energy, because when you talk about change in internal energy, that means you are going from one temperature to another. So we normally say that internal energy is a state function. What do we mean by when we say it's a state function? In a layman's word, it means it's a mathematical function. So there's a mathematical function that you can use to relate different state variables in relation to the equilibrium. So you have different states of that system that you can actually use to determine the internal energy. Of course, it can go from melting, from boiling to melting, or from solid to liquid. So that is why we say that it's a state function. It's a mathematical function that relates different state variables. That is from one state to another. So that is why we say that internal energy is a state function. You can only get the change in internal energy, but to get the absolute value of internal energy is very difficult to obtain. So a state function depends only on the present state of the system, not on the path that system took to reach that state. What do we mean by that? If the state of that system is now in a liquid state, so we are going to determine that state in that present situation. We are not really interested in the path it took to reach that state. Was it by melting? Was it by boiling that it got to that state? So your internal energy, for you to be able to get your change in internal energy, is usually the initial from the final. That is the internal energy of the initial and the internal energy of the final. It's just like relating it to your product and the reactant. Of course, here, as I told you, our thermodynamics, we are more interested in chemical reactions. So we are going to be seeing more of chemical reactions, which has to do with product and reactants. So change in internal energy is going to be your internal energy of the product minus internal energy of the reactant. That will give us the internal energy. And how do you get this internal energy? Of course, is by doing work. That means when you supply heat. So it's going from one state, from one form to another. So internal energy can be changed by doing work or supplying heat. When you supply heat, the reaction is actually going from, so you are going from reactant to product. So with that, you have difference in energy. Of course, the energy of the reactant will definitely be different from the energy of the products. So we'll now look at first law of thermodynamics. We just explain this in a simple term, which I know most of you are used to. In its simplest form, it says that neither matter nor energy can be created or destroyed. So you can neither create matter and you cannot destroy matter. It's already there. You can only change from one form to another. So the first law of thermodynamics is also known as the law of conservation of energy. From the word conservation of energy, what it means is that energy can neither be created nor destroyed, because it's conserved. When you conserve something, so that thing is, you can't spoil it, you are conserving it. So that is the first law of thermodynamics. You can say the first law of thermodynamics or the law of conservation of energy, which states that energy can neither be created nor destroyed, but it can be transformed from one form to another. What is the reason? The reason is that energy can exist in different forms. So because energy can exist in different forms, that is the reason why it can be converted or transformed from one form to another. So what it means is that energy cannot be created from nothing, and energy cannot be reduced to nothing. It can only be transformed. Again, the amount of energy in the universe is constant. So because it's constant, you cannot add, you cannot remove. God has already put it there. The only thing is that we can now, because we are chemists, we can now convert it from one form to another. So the amount of energy in the universe is constant. It is very, very important that you know this. It's constant. It can only be changed, moved, controlled, stored, or dissipated. And again, for your change in energy, when energy is lost to the surrounding, then your change in energy is less than 0. That is, energy is lost to the surrounding. But when the surrounding gains energy, then the change in energy will be greater than 0. Of course, the environment has gained energy, so we expect the change in energy to be greater than 0. But when energy is lost to the surrounding, then the change in energy will be less than 0. So now, we are going to look at a closed system because we are going to be carrying out some calculations involving a closed system. For a closed system, the change in energy is your heat absorbed plus work done. So this is the formula for our closed system because we are going to be carrying out some calculations using our closed system. So we also look at some sign conventions because during your equations, you might be seeing some signs. So what does the sign mean? Once they say heat transfer in, that is endothermic. So what it means is that your heat absorbed is positive. Heat transfer into because this is our open system. The change in energy is equals to your heat absorbed plus work. So when heat transfer is in, when you transfer heat into the system, of course, we know that that is endothermic. When heat is transferred out or given to the surrounding, then that is your exothermic reaction. Of course, for heat transfer in, that is endothermic, you have your plus heat absorbed, and this is negative, the heat given off. Also, you can also have transfer in work. When it's transferred into the system, is positive, and when it's transferred out, it's negative. So it's very, very important to know these sign conventions because when you are given an equation and they say heat is transferred out or heat is absorbed, you should be able to know if it's going to be positive or if it's going to be negative. In a situation you are given the value, let's say you are given a value of 300, and when you want to carry out the calculation, they say that the heat is given out. What it means is you are going to add a sign to that value that has been given to you. It's not going to be either positive or negative based on the question. So a sign convention is very, very important to know if it's going to be endothermic positive, exothermic negative, or heat transferred in based on work, or heat given out based on work. So let's look at a concept check. You say calculate the change in internal energy. Your change in internal energy, sometimes you can see it as change in U or your change in E. It can be E, it can be U. So your internal energy. So calculate E. You see here is E, but here we are using change in U. So as I said, your internal energy, sometimes you can have it as change in E or change in U. So calculate E for a system undergoing an endothermic process in which 15.6 kilojoule of heat flows, where you have 1.4 kilojoule of work done on the system. So change of course, this is for an open system. So that is why I gave you that equation that will be working with the equation. The change in U is equal to Q plus W. So we are going to use that to carry out this calculation. So we know that our heat absorbed is 1.56 kilojoule. And because the process is endothermic, they say heat flows, and where your 1.4 kilojoule of work is done on the system. So what it means is that because heat flows in, so it's endothermic. So that is why this value here is going to be positive. So we are going to our change in internal energy. Our change in energy is going to be your Q plus W, which will give you 17.0 kilojoule. Now let's look at another one, another concept check, another calculation, still based using our change in internal energy. It says when a spring was wound, 100 joule of work was done on it, but 15 joule escaped as heat to the surroundings. What is the change in internal energy of the spring? So now we are given that the work, the W is 100. So what is going to be our Q? Is it going to be this value here? Is it going to be positive or negative? Put it on the group chat. So you see that our Q is going to be negative. So delta U is going to be Q plus W. Because they say 15 escaped. So what it means is that it's an exothermic reaction. So it's going to be, that is why we had to add negative to the 15 joule. So that was what I was trying to explain the sign convention to you, because we are going to be needing them when you start calculations. So you know, is it endothermic or is it exothermic reaction? So your change in delta U is not going to be minus 15 plus, of course, the work, our work is 100, which will give you 85 joule. Mind you, if you miss putting negative sign in this 15, you know your answer is going to be 115. So the sign is very, very important when you are carrying out your calculations. So when I look at entropy, what do you mean by entropy? It's a measure of the total energy of a thermodynamic system. So we are looking at the total energy in that system. So it includes the internal energy, the amount of energy required to make room for it by displacing its environment and establishing its volume at a constant temperature. So when you're talking about entropy, you're talking about the total amount of energy. You're also in relation to the volume and the pressure. So we have our entropy, which is your H, is equals to U, the internal energy, in relation to your volume and the constant pressure. Both your volume and your pressure is at a constant. So just like internal energy is difficult to measure, your entropy, absolute entropy energy, is also difficult to measure. But what we actually do is to measure the change in the initial and the final entropy. So that is actually how we'll be able to get the entropy of whatever thermodynamic system you are studying. Absolute entropy value is difficult, just as we talked about our internal energy is difficult. But when we now look at it in terms of initial and final, that is the reactant and the product, then we'll be able to measure the entropy of the thermodynamic system. So your delta H, your H is the final entropy of the system expressed in joule. Also, your H initial is the initial entropy of the system. Both of them are expressed in joule. So we have to be careful when we are carrying out our calculations to be sure that both carry the same units. So the change in entropy is also the heat of reaction at constant temperature. So your change in entropy can also be the heat of reaction at constant temperature. This is the heat absorbed at constant temperature. So let's look at some entropy of reaction, because we are going to carry out some calculation. So as I said, the entropy change is the entropy that is associated with our chemical reactions. Of course, this is the number of moles of the product, minus number of moles of the reactant. And for it to be positive, so we have to have if your delta H product, if your H product is greater than the reactant, then your delta H is positive and the reaction is endothermic. Always know that when your reaction is positive, then it's endothermic. Why? If the enthalpy for the product is less than the enthalpy for the reactant, then your delta H is negative and the reaction is going to be exothermic. So we have this here. So for reaction pathway, we have our reactant. So for it to go to product, it must cross this barrier, and this is what we call the activated complex. What it means is that you must supply heat. You must be able to supply heat energy that will be able to cross for the reactant to overcome this activated complex for you to be able to form the products. So for this, this is an endothermic reaction. So it's going to be positive. Why for this? You see that your product is actually less than the reactant, but here your reactant is greater than your product. So that is actually what will give us if it's going to be positive or if it's going to be negative. So here your reactant is starting at 100 and we are getting a product at about 300. So if your H product is greater than your reactant, delta H is positive and the reaction is endothermic, while the reverse is the case. So we look at some equations. So these are some balanced chemical equations that show the associated enthalpy change. And these are called thermochemical equations because it's actually showing the enthalpy change. So here we have our cesium reacting with our oxygen. Of course, your cesium is in liquid, L here is showing liquid, and your oxygen is in gaseous form to give us a CO2 plus SO2. Our delta H here is minus 1072 kilojoule per mole. Or you can also have a situation where you have your cesium plus your oxygen to give you your CO2 and your SO2. This is now giving us a positive value. So what it means is that one is endothermic and the other is exothermic. Now, sorry. You can also have a situation where both of them will also have the same, where they have the same value. Of course, this is 1072 and this is 1072 too. But the only difference is one is exothermic and the other is endothermic. You also have that your water is going from liquid to gaseous. And here your water is going from liquid plus energy to give you your gaseous form. So this is actually your endothermic. And because this is added, so we expect this to be exothermic. So you have here your aluminum plus your iron oxide to give you this equation. And this is actually an exothermic reaction. So characteristics of H. As I said, sometimes your H can be your heat of reaction, so in that instance, you're looking at both the internal energy and the enthalpy function. So this means that they depend on the state of the system and not on how it's being achieved. As I told you, it's not whether you got the system from liquid to melting or from melting to gaseous. It actually depends on the state of that system at that particular time. Is it in the liquid state? Is it in the solid state? For example, we gave a good example here. When you cook your rice, it does not matter whether you cooked it by boiling, in the oven, in the kerosene. Regardless of how you cooked it, the internal energy is going to be the same. So we say that most times your internal energy is extensive. So when we say it's extensive, this time around, it has to deal with the amount of the substance you are dealing with. So this means that they depend on the amount and state of the phase of that substance. For example, if you have 5 grams of rice and 10 grams of rice, of course, the internal energy, the amount of energy you are going to use to cook 5 grams of rice is going to be different from the amount of energy you are going to cook 10 grams of rice. So 5 grams of ice has a different internal energy from 5 grams of water. Likewise, 5 grams of rice will have different internal energy from 10 grams of rice. What is the implication? Let's see the implication. The implication is in terms of the energy. So here we have our graphite. We have our CO2, which can dissociate into our graphite and our oxygen. If you check here, the heat, the standard enthalpy of formation, which is this, is 10. But now, if you have 2 of your CO2, of course, it's going to affect the number of moles of the products. So here you see that you're now having 220. So here you have just 1 mole of your carbon, giving you 1 mole of your graphite, and there you have 1 mole of your oxygen. So the standard enthalpy of formation here is 110. When you now have 2 moles of your CO, your carbon monoxide, you see that the standard enthalpy of formation has also increased. I don't know, my system is hanging. Sorry. Okay. So here we have our water, liquid going to gaseous form. The heat of vaporization, this is the standard enthalpy for vaporization, is 40.66 kilojoule per mole. Now, when it's going from gaseous to liquid, we now see that heat is given out to the surrounding. So what do we have? The values are the same because, of course, this is liquid to gaseous, and this is gaseous to liquid. Both of them are the same. Their molecular formula is the same. But because here heat is absorbed, so you are having a positive value. Why for this? Because it's going from gaseous to liquid, then heat is given us. So this is one of the consequences of the first characteristic, that is the H, the change in internal energy. So let's look at some calculations. Concept check. How much heat is released when 4.5 grams of methane gas is burned in a constant pressure system? So this question, what is actually saying that this is your methane gas burned in oxygen. So it's giving you your CO2 and the water. And the delta H is minus 890 kilojoule per mole. So what it means is that it's actually 1 mole of your methane that gives off 890 kilojoule per mole, because you say how much heat is released when 4.5 grams of methane gas is burned in a constant pressure system. So what it means is that from this equation, you see that it's 1 mole of methane that actually gave us this. But now they're asking us to calculate how much heat will be released if we have 4.5 grams of methane. First of all, we need to know the number of mole, because what we have here is kilojoule per mole. So, and this is for 1 kilojoule per mole. So we are now, because we are going to, our answer is going to be in kilojoule per mole, we first of all have to know the number of moles for your 4.5 grams of methane. And doing that, of course, we know that number of mole is equal to mass over molar mass. So the mass is 4.5 over the molar mass, and that will give us the value. So whatever value we get here, we actually multiply by 890 kilojoules. So whatever value we get is going to be in a kilojoule. So the heat given off will now be this number of moles multiplied by this energy. So that will give us 250 kilojoule. Please, are we together? Are we together? Well, I want to assume that you can hear me. So let's look at another concept check. This one says, when 2 mole of hydrogen and 1 mole of oxygen react to give liquid water, 572 kilojoule of heat evolves. So this is the question. So because 572 kilojoule of heat is given off, you see that in the equation, we are now adding a negative sign. So 2 moles of hydrogen reacting with 1 mole of oxygen will give you 2 moles of water. And we are told that 572 kilojoule of heat evolves. So heat is given to the surrounding, and that is why we have it as 572 kilojoule. So the question is, what is the amount of heat evolved for 1 mole of water? This is just a simple calculation. You don't even need, if 2 moles will give you minus 572 kilojoule, what will 1 mole give you? You just divide this by 2. That will give you 286 kilojoule. So this is just a simple calculation. So I don't really need to go. So chemically, what it means is that 1 mole of hydrogen reacting with 1 mole of oxygen will give you 1 mole of water. So because here we have 2 to 1 giving us 2. So you can, by equation, you can actually solve this calculation. And also, you can just multiply, divide by 2. And there, that will give you 286 kilojoule. So I don't know if we still have time. Oh, our time is up. So do we continue or do we stop here? They are saying continue, stop, continue, stop. Yes, you are going to get the slide. Continue, stop here. But you know, today is supposed to be our last lecture. So I will still need 1 more lecture to complete this course. I will need 1 more lecture. So we'll just continue for like, let's say just 5 minutes. Let's just continue for like 5 minutes. So we look at, so we'll now talk about calorimetry. What is calorimetry? It's the science of measuring heat. When we talk about science of measuring heat, it's actually telling us that it's a process of measuring the amount of heat released or absorbed during chemical reaction. That is just it. Calorimetry is just when heat is released to the environment or heat is absorbed into the system, the process of measuring that amount of heat is what is that science is called calorimetry. And again, it is based on observing the temperature when there's a change in air, when there's a change in body temperature. And the instrument we use in measuring calorimetry is called a calorimeter. A calorimeter is used in measuring calorimetry. You want to measure the amount of heat absorbed or the amount of heat given out, you use your calorimetry. And it depends, and it's for you to be able to measure it, you must know the volume and the pressure. So it must be done at constant volume or at constant pressure. So Constant volume calorimetry measures the internal energy, while the constant pressure measures the enthalpy. So there are two different things you are measuring using your calorimetry. What are they? You are measuring the internal energy. Sorry, you are measuring the internal energy. You are also measuring the enthalpy. So the internal energy and the enthalpy, both of them at constant pressure. The constant volume measures the internal energy, while the constant pressure measures the enthalpy. Now, if you measure the constant volume, if you measure the constant volume, what is called is a bomb calorimeter. So a constant volume calorimeter is called a bomb calorimeter. What about if you measure a constant pressure? What is it called? Do we know? It's called a coffee cup calorimeter. So a constant pressure calorimeter is called a coffee cup calorimeter. I know most of you will not, when you remember the word coffee, you know that it's talking about a constant pressure. So let's see, let's do one check, concept check. You say, when a student mixes 50 ml of 1 mole HCl and 50 ml of 1 mole sodium hydroxide in a coffee cup calorimeter. So what kind of calorimeter measurement is this? Put it on the group chat. You say when a student mixes 50 ml of 1 molar HCl and 50 ml of 1 molar sodium hydroxide in a coffee cup calorimeter. What type is this? What is it measuring? Is it pressure or volume? Just put it in the group chat. Everybody. Good, thank you. The temperature of the resultant solution increases from 21 degrees Celsius to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoule per mole HCl. So this is the one we are calculating. Assuming that the calorimeter loses only a negligible quantity of heat, that the total volume of the solution is 100 ml, that its density is 1 gram per ml, and that its specific heat is 4.18 joule gram per Kelvin. Now, based on this, what formula are we going to use? It has already told us that its specific heat is 4.18 joule per gram per Kelvin. So you agree with me, we are going to use our specific heat capacity. That is our CS is equal to what? I would have asked you to put the formula on the chart. So we have our HCl, but just know that we are going to use the formula for our specific heat capacity because it has already given us our specific heat capacity. So we have our HCl plus our sodium hydroxide, of course, it will give you water and the sodium chloride. The total volume of the solution, we are told, is 100 ml. Now the mass is, so because we are giving density, we can use our density to calculate, to get the mass. Because for our specific, let me show you what I mean. Because for our specific heat capacity is our Q, heat absorbed, the mass, and the change in temperature. So that is why we need to get the mass. And we can get the mass by using what? Density is equal to mass over volume. Our density is 1. Density is 1. Density is 1. The volume is 100. So with that, we'll be able to get the mass. So if you do your density is equal to mass over volume, your density is 1 is equal to mass over 100. So if you cross multiply, that will give you 100 grams. So that is how we got this 100 grams. And the temperature, the change in temperature is 21 degrees Celsius to 27.5 degrees Celsius. And again, let's look at it. It says that the temperature of the resultant solution increases from 21 degrees Celsius to 27 degrees Celsius. So there's increase in temperature. So it's exothermic. So there's increase in temperature. Energy is given out to the surrounding. So we say that since the temperature increases, the reaction must be exothermic. So your delta H will be negative. So our formulas, so the delta, so why we have negative here, this negative is actually for this change in temperature. So recall as I told you, we are going to use the specific heat capacity, which is the heat absorbed over your mass multiplied by your delta T. We already know our mass using density is equals to mass over volume. So if you do this calculation, you are going to get minus 2.7 kilojoule. So it's 2.7 times 10 raised to each, that is in joule. But if you now convert to kilojoule, you now have 2.7 kilojoule. So our Q is going to be as, so because it's at constant pressure, so what we are calculating is Q. So our delta H is equals to Q is equals to minus 2.7. Mind you, there was a place I told you, let's see if we can still recollect, that, let me see. There's something I want to draw your attention to. I don't know if I can see it. Sorry, there's something I want to draw your attention to. I don't know if I can see it. Sorry. So I'm coming. There's something I want to draw your attention to. Why we saw delta H is equals to Q there. Okay. So this is what I want to draw your attention to. If you remember when I said the change in enthalpy is also the heat of reaction at constant temperature. So your delta P, your delta H is equals to heat absorbed. This is your heat absorbed at constant pressure. So that is why, if you look at that final equation we are looking at, we said that delta H is equals to QP. So we are looking at the heat of reaction at constant pressure, because that is what we are asked to calculate. That is what you are looking at. Okay. Okay. So that is why, so because it's a constant pressure process, your delta H is equals to Q, which is equals to minus 2.7. So I just wanted to draw your attention to why we are equating it to Q, because we are looking at constant pressure. Now, mind you, we were asked to calculate, this calculation is what? We say when a student mixes 50 ml of 1 mole HCl and 50 ml of 1 mole sodium hydroxide, he said calculate the enthalpy change for the reaction in kilojoule per mole HCl. So we already have our calculation using your specific capacity. We've already obtained our answer in kilojoule, but we need to get it per mole HCl. So what do? So of course we have to look at expressing it per mole HCl. So to express it per mole HCl, we already know the concentration. The concentration was 1 molar, while the volume was 50. So I've tried to use it here. So concentration is equal to number of moles over volume in dm cubed. The molarity is 1 molar, the number of moles, and our volume is 50. So that is 0.05 moles per dm cubed. So that is how we got 0.050 liters. So of course, our number of moles is going to be our concentration multiplied by what? Volume in dm cubed. Of course, the liter, we cancel the liter. And that is how we got our 0.050 mole. So whatever we are going to get is in mole. So our delta H, from what I did here, is now going to be minus 2.7 kilojoule. That is the answer we got, divided by your 0.05 mole. And that will give you minus 54 kilojoule per mole. So our delta H, the final answer to our question, is actually minus 54 kilojoule per mole. So any question? Do we have any question? So I want to stop here. So please, when can we have our next lecture? I need a time for the next lecture. Tomorrow, next time. Tomorrow I start today. Next week, Monday, another lecturer is coming up to start. Today, I'm not free again today. So please, just across to me, the class reps. Agree on the time, but today I'm not free today again. I'm no longer free today. Monday 9 a.m. is out of it because another lecturer is coming up. So just fix a convenient time, just fix the time and get across to me. We don't even need up maybe like 45 minutes. We'll be done. They are saying Sunday. Okay. No, Sunday is out of it. What is, how can you be saying Sunday? I'm going to send the slides to you, definitely. You have a question. What is your question? You said, "Ma, explain the last part. Is the specific heat negative?" Yes, it's negative because we said that the final answer is minus 2.7 kilojoule because from the delta H, the delta T, we are going to have a negative because energy is given off to the system. That is why we have the negative sign there. So the questions on the chat, I'm trying to answer them. On Monday, I'm free. On Monday, I'm free. So I'm free the whole of Monday. But we can't have it 9 because another lecturer is coming up by 9. So the whole of Monday, I'm free. So just let me know the time on Monday so we can just complete it. Monday, 3 p.m. Fair enough. You said there was the degree Celsius. No, it was in degree. We did not convert. It was in degrees Celsius. You only convert if you are giving the question in Kelvin. That is when you convert. But if it's in degrees Celsius, you just do the subtraction. So let's say Monday by 2 p.m. or 3 p.m. is fine by me. So just for Saturday and Sunday is off. Monday is okay. 2 p.m., 3 p.m. Monday is fine. Let's say 3 p.m. on Monday. So get back to me if 3 p.m. on Monday is okay. The degree Celsius in the last question, was it converted to Kelvin? No. Is the specific heat negative because it's an endothermic reaction? Yes. Because, yes. Okay, so we'll see on Monday. On Monday by 3 p.m. if it's okay by you. So just let me know. So see you on Monday. You said some people have lab by 3 p.m. on Monday. Okay. Just get across to me. Let me know when it's okay with you. But my Monday is free. Monday is free for me.